Today, we want to determine water to cement ratio. So, two things. To know water to cement ratio, we have to consider both strength and durability. In the quiz last time, you answered why. Because as you can see, water to cement ratio, it changes the strength dramatically, and also because it changes the porosity, it also has a big effect on durability. So we need to consider both into account. So there are curves like that where you can, if you know what you want for compressive strength, you can kind of design water cement ratio. And as you can see, if the material is air entrained, the strength is lower. This was also some part of your quiz. When you add more air, the strengths go down when you have more air content. But we like air entrainment because of durability. Now, if you just focus on the strengths, there is a table which gives you what compressive strengths at 28 days, and then depending on whether you are using air entraining agent or not, you decide on water cement ratio. It turns out that we can't just use the 3500 psi design just like that and say, okay, I just interpolate between 3000 and 4000. I know it is air entrained, so it will be the average of these two numbers. It turns out that this is not what we do it. And the reason is, what you get when you say 3500, if you choose this as your design compressive strength, that would literally mean that half of your material has lower strength than 3500 and half will have more because of the normal distribution which you have seen in statistics. So if you just take 3500 here, half of the concrete that you are designing will have lower strength, and this is not desired. So if you know the standard deviation, what you do, you say, no, I design not for F prime C, but I add 1.34 standard deviation. So this is standard deviation. If you know it, how do we find out the standard deviation, you think? Well, either you are given that for the design process. If you want to find it out, you basically get a bunch of, you make a bunch of cylinders, you crush them, and then you calculate the average and the standard deviation. This is how you would find it out experimentally. If you know that, so your design won't be for F prime C, you add 1.34 times the standard deviation. And if you do that, then 90% of the material you are designing will have a strength greater than 3500. I hope this is clear. Statistics is a prereq for this class or concurrent. So if this is clear why we have to add 1.34. Yes? We do that to increase the safety factor in a way. If you don't know anything about standard deviation, you are not given anything, any information, then there is a table which helps you to add kind of another number to that, to basically to find out, to increase your design strength. So you don't go with 3500, you bump it up a little bit to make sure that most of your material is going to have actually this kind of a strength. So this is kind of the thinking behind it. In this case, we are not given a standard deviation, right? So we just look to see, okay, What we have is between 3,000 and 5,000, so we add 1,200 psi to it. So then, this will be your compressive strengths that you use in the table. If you were given a standard deviation, in the example on Friday, we are given that, then you would add 1.34 times standard deviation. And again, make sure you understand why we are doing it. We are doing this to make sure that most of our material has a strength equal to 3,500 or greater. You don't want to go with 50% of your material weaker than the design strengths. So this is the reason. Questions? So once we have this number, then we can go back to the table I showed you in the beginning. And now it is for the 700, and you need to interpolate. So whenever you don't see your number in this table, you need to interpolate between these two numbers. You see that it's closer to 5,000, so if you do the interpolation, you get 0.42. And we are not done. This is only based on strength. We still have to look into durability. So this material is going to be air entrained. If you remember from last time, it has severe exposure to freezing and thawing. And you look at 4700, this is the boosted compressive strength after taking into account the variability in material properties, right? We added 1,200 to 3,500. And then you have to interpolate. And you get here. Now we have to look durability. So there are also tables which gives you some idea how to choose it for durability. And one table is the next slide. So here, you see now you have a maximum water to cement ratio for different exposure, for example, corrosion. Look back at your problem if you have forgotten and convince yourself that this is a good choice. Just looking at the durability. If you didn't have a specified strength, then you had to make sure that this is also valid. But your job requirement is different, and that's fine in design. It could be like that. Any questions? We are not done. There is also sulfate. So the durability includes freezing and time, which we consider by looking into air entrained column. It includes corrosion and also sulfate. So when you go, you also find another table. You see all the references to the table are given. You know where they are in the book. You can also print it out for the exam, just tables in the notes. That's absolutely fine. And then you see that basically for a moderate exposure that we have here, you can have a maximum 0.5. Now my question is, put everything together and design your water to cement ratio. Now we have a value for a strength, we got a value for corrosion, we got a value for sulfate. What do you choose then? Work on this on your own with your neighbors, look back at the problem. So sorry that I cannot make the quiz, but don't worry, like the quiz today, for example, has extra credit. Okay. I'll give 2 more bonus quizzes. Okay. So at the end of the semester, try to make it. Okay. So you're not going to lose anything.
Thank you for getting back to me so quickly.
Well, finally.
sulfate attack. What do you choose then at the end? Each one. So in the slide, try to summarize. Okay, for strengths, you got 0.42. For corrosion, for sulfate, if someone has the answer, raise your hand so I can check. I haven't seen it. One correct answer. So I've seen 3, so I can. So when we just consider strengths, we get 0.42. I gave you a graph and a table. You don't need to use both. You can either use the graph or the table. So for durability, we had corrosion and sulfate and freeze-thaw, and you see that this is 0.4, this is 0.5 maximum. So you want to have the lowest water to cement ratio as possible, because remember, lower water cement ratio means higher strength, better durability. So you don't want to design for something which is less than one of these. So you need to choose the minimum of all 3, which is in this case 0.4. So now we have designed our water to cement ratio, and we can start calculating. We know the maximum size of aggregate, slump, we decided on last time. We got now water to cement ratio, and we also found the amount of water in one table. If you have forgotten, which I guess some of you may have, look back and see that we have found the water in one table before with slump and with MSA. Any questions about designing water cement ratio? Great. Fantastic. So we are done with that. We move to the next step. And that's calculating the amount of cement. Go back to your notes and see that in the table, we found the amount of mixed water, assuming that aggregates are in SST condition. Don't forget that. This is just mixed water, assuming SST condition for aggregates, both fine and coarse. This was in a table. We had MSA, slump, and then we found this. And if you know water cement ratio and you know how much water, then you can calculate the amount of cement. we know how much cement. Why do I say pound per cubic yard? Do you remember still from last time? What is this cubic yard in the denominator? We designed everything for 1 unit volume of concrete, and we chose it to be 1 cubic yard. It can be something else. So that's why everything comes in pound per cubic yard. And if this is pound per cubic yard, also this is weight. This will be also pound per cubic yard. So we are done with these two. That's great. Step number 6 is also completed. Now we have to find coarse aggregate content. Here we need to use another table again. There are a few details about this table important to pay attention to. And the most important one is that this gives apparent volume, this table. And to design for the coarse aggregate content, you need to know maximum size of aggregates, and you need to know fineness modulus. Go back to your notes and see what fineness modulus was. In one slide, you have summarized all the information. What was the maximum size aggregate? This we designed. 3/4 of an inch. And fineness modulus was 2.7, which doesn't appear on this table. So all you need to do is to interpolate. Here is easy. You just take the average of the two. Right? This is what you do with the tables. So what you get would be the average of these two values, which would be 0.63. And remember, look here what it is written. This is apparent volume of coarse aggregate per unit volume of concrete. It is volume, right? It is basically, if you took 1 cubic yard, how much coarse aggregate this table is suggesting? How much? What is this 0.63? So it is apparent volume per unit volume of concrete. So it's 0.63 cubic yard. It's kind of a percentage. So this is apparent volume. But what we need is actually weight. So you have information about coarse aggregate. Calculate your weight. What you have is the volume. You have the dry rod and unit weight. If you look at your summary information, I ask you to look at table. Something should be written there to that end. as a review in the beginning. Hold on. Sorry. I tried to have someone. It's very helpful if for Friday you can prepare your tables, etc. for concrete mix design. So when we solve the second example, we can kind of simulate what the situation would be during the exam. Try to organize it so you can find things. That would be very helpful. Because in the packet for Friday, there is no tables. You need to use this packet. Or you need to, I suggest that you bring your tables. So, I first calculate the feet, cubic feet, because the oven dry rodded unit weight is given in pound per cubic feet. If you have done it differently, that is absolutely fine. Basically, you have the dry rodded unit weight, you have the apparent volume. You need to go from cubic yard to cubic feet. Given this information is in this packet. And then you just calculate the weight of the material. Remember that this is oven dry. And now we have to calculate it at the air dry and SSD. If you have that information, you should do. You have the moisture content and you have the absorption. So kind of what you learned in aggregates, now you have to put into practice. Now you need to calculate, this is the oven dry. That means that all the moisture is gone. Now you have the moisture content and absorption, which is moisture content at SSD condition. And you've learned how to calculate the rate. So now it's the time to use that knowledge. It's fine. I've pre-done this, so I cannot change it. Again, if you write everything in one line, it's fine. You don't have to do it in 2 seconds. Now calculate the moist. You have the moisture content. How much is it for aggregate? It's 1.2%. So now you know that if it is completely dry, it weighs this much. If it is 1.2% moist, how much does it weigh? Remember moisture content? The definition is very simple. No? It's the weight of water, which is the waste of material, which is moist. Minus the solid material, so here. Really no need to memorize it. It's kind of, okay, how much water you have, which is how much is your material heavier because of the moisture than the oven dry over the oven dry times 100. What you know now is WS. This is what it is. What you want is, what is the weight with 1.2% for air dry and 1.5% I believe for the SSD. You need to calculate this. Let's just learn it in the class. There is no reason to not to do the exercise with me in the class and try to spend more time at home. It's much better to just spend some time, right? So I have first SSD. If you substitute here WS, this is how what you get here. You can write this equation like this. MC in percentage plus 1 that's what it is. Nothing different from here. If you just use that equation, you get absolutely the same thing. This is over, this is 1. And what you are looking for is this W sub M. You can use the equation, you can use this shorter, it's all good. I saw some correct answers, so I'm hopeful that it's not. Anyone has a question about this? What's going on here? So we get the volume from the table. This happens to be apparent volume. This is what the code is giving us. So you need to have dry rodded unit rate. Because remember, this was based on apparent volume versus densities which were based on absolute volume. And what you get in terms of weight is oven dry. It's completely without any moisture. You know the moisture content and you know absorption. Absorption is moisture content at SSD condition. So you can calculate the weight at different stages. And we have studied this in aggregate, so I hope that you are okay with it. Okay. We are done with this step, and we go almost to one of the last steps, and that's how to calculate the amount of sand. This turns out to be very easy. So first we have to find how much is the absolute volume of each component in 1 cubic yard of concrete. So starting with cement. We calculated how much cement we have in terms of pounds, but we didn't calculate the volume. But this is not a problem because we all know that the specific gravity of cement is 3.16. So it's very easy to go from volume to weight to volume. Now we do have to do the same for water and for coarse aggregate. and also for air. So the idea is we calculate the absolute volume of each component and we say we fill the rest with sand. This is the idea. So let's calculate the absolute volume for coarse aggregate. Now then we need to use as a specific gravity. You know how much it is, how much is weight. Then we can calculate using a specific gravity. Depends on what specific gravity So for coarse aggregate, the bulk specific gravity which is given to you is in SSD. So you need to use the correct weight for that. Has everyone taken homework 7 and quiz 7? Yeah. So you here. But everyone has looked into the homework 7 file. The middle, how much it go from here to here and this to here? Volume of water. Don't wait on me. Let's calculate the volume on the right. And volume of air, don't forget, air doesn't have weight, but it has volume. At some point, we selected the air content. We know what the air content is. And you want to see how much of the 1 cubic yard is air. And sometimes they don't use it after the order. the weight, we have the density, and we know that specific gravity is based on absolute volume. And why I'm using here SSD weight for coarse aggregate, because what you are given in your problem, if you look what you have from your job title is SSD specific bulk specific gravity. And then air. So basically everything you have so far, if you know the weight, you calculate the absolute volume. Why it is 0.06? Because it was 6%. And the 27 cubic feet is just 1 cubic yard. So I'm just saying, okay, this is 6% of that. And this is SSD because this is SSD bulk specific gravity. And once you have all of that, you say that, okay, whatever is left in my bucket, I need to fill it up with sand. So the whole thing is 27 cubic feet, then 7 water, coarse, and air. And you see that the air is not insignificant in terms of volume. I hope you will pay attention that the air is not really insignificant. Now that you have the absolute volume, so this is absolute volume of sand. Now you need to calculate the weight of sand. Look back at your information table in the beginning and see what you have and what you can calculate. Remember, you need to have the weight, oven dry, air dry, and SSD. So depending on what the specific gravity you have, you start and then you use moisture content to calculate. You need now to calculate the weight. Looks like the quiz has to wait for Friday. It's a bonus quiz. Towards the end of the semester, always give bonus quizzes, so it increases your grade. You need to calculate the weight at SSD condition, oven dry, and air dry. So we need to start with SST because this is what you are given, a specific gravity. And once you have that, then just like before, now you have to go from SST to dry condition, 1%, and to natural moist condition, based on the moisture content that you were given before. You need to be very comfortable with these calculations that you regularly do. And remember, I was emphasizing that because you need it. And now we're almost done. On. So this is 1% absorption, 0.6% moisture content. How many had calculated this right? I saw a few, but okay. Has everyone written down what you need to write down? Because we need to go through this last stage, and this is adjusting for different levels of moisture. So remember that now you set up a table like that. The water that you have is for SST condition. If your material is coming at a different condition, this is not the amount of water you can use. So you want to first sum this up, and now it is easy because you have the weights. You can just subtract them and see how much deficit or how much extra water you have and correct the amount of water. So it's kind of easy right now to do it. But we need to do this, so you need to fill up this table. You will see in the exam also there is a table like that, you need to fill it up. So it looks just like this. Now in moist condition, this is kind of a review what it is, and here are the moisture and absorption for this problem that we have. So if you look at the difference between SST and moist weight for coarse aggregate, that's the deficit. In this case, we have deficit. For coarse aggregate, you have deficit for sand. So since you have deficit, if you are using them at air dry condition, you need to add to your water these two deficits. And exactly the same thing if it is oven dry. Because this much of the water, like 9.2 pounds, will be just used to bring the aggregates to SSD condition. And then the rest, 305, will be available for mixing. Clear? This is what I'm talking about. And exactly the same thing you do for dry conditions. So you look at this difference, you can even look at this, and it's a good idea to check the total, and it should be the same. This is like a double check that you haven't made any mistake in calculations. Because at the end, this should be all the same amount of batch. And once you have that, you are pretty much done with your design. And this is what you would consider your design. And typically what people do, they make a trial batch, they wait 28 days, they make cylinders, they crush them, get compressible strengths, they calculate air content, and they check. They check that they have achieved the design goals. And then if there are some discrepancies, you'll adjust. And then you are done with your mix design. For Friday, it will be very helpful.